Alright, so hello everyone. Today we are going to have post-contest discussion for Leetcode Weekly 411. We'll be discussing all the 4 problems. So let us start. Problem 1. Count substrings that satisfy k constraint 1. Alright, so this is like the first part of the main problem. Or sorry, not the main problem, as you can say. There are 2 parts to this. There is the one part and then the fourth problem is that the second part. So this is a pretty easy problem, right? It's basically implementation by looking at the constraints. Let us look at the problem. You will be given a binary string s and an integer k. A binary string satisfies k constraint if either of the following condition holds. That is, either, that means either of these 2 points are, either in that string you have at most k zeros or you have at most k ones. Now, return an integer denoting the number of substrings of S that satisfy this k constraint. Now, looking at this question, it's very simple that if you are given a string and you're talking about some substring in that string to be checked, then I know that if I have a lower constraints, this is for the beginners out there, if you look at the constraints over here, S dot length is 50, which means I have a very small length to iterate into. So if I have a very small length to iterate into, what I can do is I can actually run a brute force solution which is going to help me go to every substring. And then when I go to every substring, I can easily check or count what is the number of zeros in that substring, what is the number of ones in that substring. And if I see that any one of the condition is fulfilled with respect to the maximum limit k on both the counters, then I know that substring can be counted as an answer to this problem. Alright, so a very, very simple problem once you understand the constraints, right? If this would have been higher constraints, maybe we could have come up with a different solution. But for lower constraints, I know I am good to go. I can very well create a brute solution and it's going to work. Alright, so let's try to look into this part. So what is my target? Let's say the string looks something like this, 101, 10. Let me just increase this limit. I think you're good to go. 1 0 1 0 1. So what is the target? My target is somehow I'm able to extract all the substrings out of this string. What is the k limit that was given to me on this? K is 1. Alright, cool. So k is 1. So I'll be like, alright, in this string, main string, if I ask you what is the, can you print all the substrings for me? So I'll be like, alright, if I start from here, then here, then here, then here, then here. These are the 5 substrings. 1 1 0 1 0 1 1 0 1 0 1 0 1 0 1. Next time I can be like, alright, now that you have covered this much limit, now cover the next up limit, and you can say I'll be starting from this position, then this, then this, then this, and then this, so on. So I know that if now I want to write the next set of substrings, they can be 0 1, sorry, not 0 1, 0 0 1 0 1 0 and then 0 1 0 1. Then I can be like 1 1 0 1 0 1, then finally 0 0 1, and then finally a 1. So these are the total count, total substrings, all possible substrings written out of this particular string. Now you can use any ideal beginner method to calculate what are the substrings getting extracted out of this main string, because at the very end what your target is, let's say once you finally achieve any one of this substring, let's say I have this substring stored in, let's say, a new string t, then all I have to do is count the number of zeros in that string, count the number of ones in that string, both of start with 0, and let's say in this string 0 1 0, I count. What is the count of zeros? Count of zeros is 2. What is the count of ones? Count of ones is 1. So I know that count of ones is at most k. So I know this string 0 1 0 has to be counted as a k constraint string because it has at most 1k, that condition is getting fulfilled. Yes, if let's say I would have taken this string 0 1 0 1, then I know in this the count of zeros is 2 and the count of ones is also 2. That means I cannot take this string because I know both the conditions are getting false. They are not getting fulfilled. If either one would have gotten fulfilled, I would have counted that. If both got fulfilled, good to go, I would have counted that. But if both are getting false, not getting fulfilled, I don't need to count that. So very, very basic and a very crude sort of a solution. Start off with a for loop. You can have a pointer over here, I equals to 0. You can say I is less than n and then I plus plus. This is the pointer that's going to run. So if let's say I have the string 10101, then over here currently I is where I have placed. Then what I want to do is I want to take up lengths. So I'll be like, all right, take up some lengths, take up 1 length, then 2 length, then 3 length, then 4 length, then 5 length. So I'll be dependent inside this for loop to create another for loop which runs int I, let's me call this as j, which is actually the length, which is initially 1, and then j can go maximum to less than equal to n minus I. Why n minus I? Because I know that if I am going to a higher limit of I then I know initially I is 0, so I want to take up 1 length, 2 length, 3 length, 4 length and 5 length. But when I moves on to 1, then I only want to take up 1 length, 2 length, 3 length and 4 length. I don't want to go till 5. That means n being 5 over here, n being 5 over here. Next time I would have become 1, so this becomes 5 minus 1, that is 4. So it kind of means that initially j has to go from 1 to 5, then 1 to 4, then 1 to 3, then 1 to 2 and then 1 to 1. So this can be the inner j thing. This is j plus plus, and then I close it up. And then what do? Inside this for loop again, I need to extract that substring. So I'll be like, all right, let me write a simple logic. String t equals to s dot sub str, that's the substring function. From where do I want? From the I index. How much length do I want? I want j length. And this is where I get the t substring now. And then again, I can run a for loop inside this t string, get the counters. For me, that would be C0 and C1, and then check if the conditions are true. Then I know my main answer can get incremented by 1, because that would mean this string t is a good k constraint string t. Now, if I talk about the time complexity, you'll be running this logic in n. This inner logic also runs a maximum time complexity of n. And this substring function will also take up n space, but this is n, and then again there's a for loop right next to it. So you can say this is n plus n. Overall, you can say this for loop is n. That's the length of the substring. So you will be running total of n cube order for the solution, which will work because we know very well that I have a n limit of 50. So if I place n as 50 inside this, I basically get 50 cube. That's all what I'm going to get, which is exactly equal to 1 to 5 and then 0, 0, 0, which means it's approximately 10 power 5. Approximately 10 power 5, right? 5 zeros, 10 power 5. So 10 power 5 solution definitely works. Not at all gives me a TLE. Yes, I'm good to go. And memory wise, I'm also good to go. So for this particular solution, since this is easy and for the beginners, a general advice, easy solutions are mostly brute forced, at least on Leetcode. So when you see first 2 problems or even sometimes first 3 problems, maybe you can try up with a brute solution, calculate the time complexity. It can happen that you actually form up a solution which runs in that brute force solution also, and you will be good to go. All right. So let us look at the solution now as instructed in the code. Take up the size of s, answer is 0. Then I check 0 to less than n. Then inner j, that's the length, 1 to n minus I, that's inner part, j plus plus. Then string t, I extract that string t, count the zeros, count the ones in this string t. I run a for loop for it, or you can say for ch, every character. If that character is 0, then I increment the count of 0 by 1, else I increment the count of 1 by 1. And then when I come out of the loop, what is my main condition? Either count of zeros is less than equal to k, or count of ones are less than equal to k. If any one condition becomes true, then I say answer plus plus. And then when I finally come out of this whole for looping, I know every time I have fully printed the substrings, fully extracted the correct substrings, and I have counted them for their condition case checking. So I know answer will give me the correct value of the, you can say the number of, k satisfying constraint strings. All right. Now, what about the time complexity? I will have a time complexity of O of n cube order, which is somewhere like 125,000 order, which roughly means I have a time complexity of 10 raised to 5 order. What about space? I'm not using any extra space. Yes. So I can say space is pretty much constant. Maybe I can say that I'm taking up some space for this string over here, but then that's not a thing that I can maybe like consider. Even if I consider that part, I know the strings are not very big. Maybe I can call that as 50 space, but that's all right. That's fine. You can say that almost I have a constant space only, because 50 is such a low number that you will be good to go anyways, right? So space is not a big deal for us. Anyways, this solution definitely passes. All right. So very easy and very direct approach problem. Let us move on to the second problem. All right. Maximum energy boost from 2 drinks. So let us read. You are given 2 integer arrays, energy drink A and energy drink B, of the same length n by a futuristic sports scientist. All right. These arrays represent the energy boosts per hour provided by 2 different energy drinks A and B respectively. You want to maximize your total energy by drinking 1 energy drink per hour. However, if you switch from consuming one energy drink to the other, you need to wait for 1 hour to cleanse your system, meaning you don't get any energy boost in that hour. Return the maximum total energy you can gain in the next n hours. Note that you can start consuming either of the two energy drinks. Alright, so let us try to understand this problem with this example. Let's say I have this array 4, 1, 1. And then I have this array 1, 1, 3. So what is this? This is basically an energy drink A. This is energy drink B. What they have given you is they have given that for every hour, every ith hour, energy drink A gives you in that ith hour, let's say this much amount of energy, and energy B gives you this much, energy drink B gives you this much amount of energy. So you're not changing different energy drinks, as in like inside this energy drink B of this array, you are drinking the same energy drink, but it's giving you different power or different, what they have termed over here, energy, right? You can say total energy at a different hour. So I can name this, I can actually index this out. I'd be like, all right, this is the first hour, this is the second hour, this is the third hour. So that means if you drink energy drink 1 or A in the first hour, you get a 4 energy. If you drink B, you get only 1 energy, and so on, so on, so on. So now your logic is to start off by first selecting some energy drink. Let's say I start off with A. And then I'll finally say, am I standing at this ith hour? Let's say I'm standing at the first hour. In this first hour, I am standing at the 8th drink. That 8th drink gives me some energy, in this case 4. So I have two options. One option is, I can be like, let me take this energy, and if I take this energy, so my energy which started off with 0 now increments to 4. And I'll be like, all right, I have drunk some energy. In this case, I had drunk the energy drink A in the first hour, and I'm good to go. So I drink first hour from A. I extract that in the first hour. Now in the second hour, remember, since I had started off with A, I'm still standing on A. So I'm still standing at A and I'm standing at over here. That means now, if let's say I choose again to drink, then I would be consuming or adding this energy for myself. I'll be adding this energy and this becomes 4 plus 1, that's 5. But there is one more option. The other option in the question is given is, what you can do is, currently, see this blue, sorry, let me not erase this. Yeah. See this blue arrow over here. This blue arrow over here denoted that you were standing at the energy drink A. But what can happen is, the person gives you, or this question gives you the power to consume, or sorry, not consume, in this second hour, have another option where now you shift from drinking energy A drink to energy B drink. And this will require 1 hour for you. So now that you have shifted, your arrow shifts to B. That means from now on, in every ith hour, the consumable energy will come from B drink because you're standing at B drink. But this 1 hour has been utilized. This 1 second hour in which you shifted, you got utilized and you were not able to gain any energy from this. And now that you're standing over here and now you're standing at the third hour. In the third hour, in the second hour you said you shifted. But in the third hour, now you said, all right, I now have the option to drink this. So I'll drink this and get energy 3. So now my total energy becomes 4 plus 3, that's 7. And I utilize this. So again, what did I do? Over here I can say third hour from B. So what did I do? I first drank in the first hour from A. Then I shifted to B. Then in the third hour, I used the B drink. So this thing which I did over here helped me gain 7 energy. And the argument is, I cannot go above 7. But the main problem over here is stating, now that we knew that I was getting 7 as the answer and somehow you formed this, but the question is, how do I code this up? How do you make sure that you report the maximum gain energy possible, by following this shifting sort of a parameter or gaining sort of a parameter, where you, if you're standing at a drink, you get two options. Either you jump to the different drink by skipping that hour. So I'll actually state this out. Option 1, drink that energy in ith hour. Or option 2 is, this is option 1. Option 2 is, don't drink that, like, don't drink, you can say, sorry, not, I cannot say don't drink. I'll say that option 2 can be skip the next drink of I plus 1th hour and move to the different drink. As in, if you are standing at the drink A, different drink. If you're standing at drink A, then you move on to B. Otherwise, if you're standing at B, move on to A, vice versa. Simple. So these are the two options. Option 1 is when you are standing at this ith drink, you drink it and you don't change your row. You don't change your drink. So drink that energy in that ith hour and don't skip to switch drink. In this case, you remain as it is in the same energy drink row where you are. If you are at A, you remain at A. If you are at B, you remain at B. But the other option is you drink that energy drink which you are standing at, like skip the, you drink ith energy drink anyways, but the I plus 1th energy drink which you could have drunk in the next hour, you don't drink it. You utilize that I plus 1th hour to jump to whatever drink you were to a different drink you are. Let's say you are at A, so you jumped at B or to A and do that part. So basically the problem is giving you two options. If you think it very clearly, this definitely makes sense. Now you cannot utilize any greedy solution in this because you have two different options. At standing at any ith index, you have two different options. You drink that energy drink and then I ask you, do you want to continue in that energy drinks rows or do you want to skip that I plus 1th hour to shift to a different energy drink? So these two options knowingly are giving you a hint that I cannot run any greedy logic. I know I have two options. That means this is indicating me towards a DP solution. Why DP? Because I know this the constraints are pretty huge. So I would have to create a DP because in this case I have two options. So this is kind of like a famous knapsack DP. A comparison, general comparison, not exactly that, but general comparison where you are kind of taking and not taking sort of a stuff. Although over here, what you're saying, our options is basically you drink that ith drink, but the option 1 is you skip two indices and you change the row, else you don't skip that indice and you remain in that same row. That's kind of like a take, not take condition, but it's not exactly the same, but you get the logic of understanding that there are two options with me I need to maintain. Now, let's come into this part. If I am maintaining a DP, then there has to be some states. So let's look into that. When we look at the options, we clearly observe states. When I know I have two options, these two options are encapsulating two things. One thing is option 1. Let's say I am standing at some ith drink. If I don't skip the I plus 1th drink, that means I remain in the same row. So look at the terms I am trying to use. You are maintaining an I variable, that's the index. And you're also maintaining what row are you currently in. So if you say that you have option 1 into picture, that means if you are at the current index that let's say this index is I, not index name, let's say this index is I, then if you are at your current index I, then you know very well that you're going to drink that drink. Let's say you are standing at current index I and let's say your row is A. So let's say your row is A. So what do? You say I will drink A of I. And then I will move on to the next drink, that's I plus 1. But do I change my row? No, my row is still A. And this is my option 1. Else, if let's say I was at row B, same thing. I will drink B of I and then I will move on to the I plus 1th R, but I will not change my row. I still remain in my row B. But what about option 2? What is option 2? Option 2 is if you are at row A, don't drink that row A, don't drink that A of I, don't drink that and simply move on to I plus 2 index by changing your row to B. What would that mean? That means I have skipped the I plus 1th hour to utilize myself to switch rows. If I was at row A, I switched to row B and index became I plus 2. And the other thing would be if you are at row B, then same thing, jump to indices and make row A. So these are the options that are given to me. And for these options to get maintained, I can very clearly see I'm maintaining two states. One thing I want to maintain is I, that is the index I'm currently standing at, or the ith hour I'm currently at. And the other thing is row. Which row am I talking about? Am I at row A? Am I at row B? So what? So if I now calculate what is the DP states, can I very well understand what is going to be the time complexity. I know that n, that's the total size of the total size I can iterate, is actually 10 power 5 order. So that means, and row, what are the total number of rows you can have? Only 2, right? Either they are row 1 or row 2, row A or row B. So can I say I have a total of 10 raised to 5 into 2 time complexity of this solution? Yes, I can say that. Why? Because the dp when will be written will obviously have the memoized solution, and dp solution in that memoized sort will be dependent on the states, multiplication of states. Since I have 2 states over here, I and rho, and the maximum those states can achieve is I can go maximum to 10 power 5 order and rho can go maximum 2 order. That means time complexity is 10 power 5 into 2. Alright, so this is going to be the whole solution. Now I will go for a recursive plus a memoized solution. You can definitely go for an iterative or a tabulative solution. That's still going to work, not going to be a problem. Recursive plus memoized might seem a better thing in this, because this is like a simple option 1, option 2 taking sort of a solution. Alright, so let us quickly look at the code piece over here. I will create a vector of vector dp outside, that's my global vector of long type. Then I will get the size, that's the size of A. I know size of A, size of B both are same, since A and B are same in size. So I get any one size, that's n. I'll resize the dp with n plus 1, and that's the total I states I can have, and total 2 rows, so 2 states. And everything starts with -1. And then what do? I'll say that I am going to call the maximum, or I'm going to return the maximum of what is the helper function giving me if I would have. Remember, look at the states. Ith index. What row am I at? Total size, A and B. So this thing is constant. I know n is the total size, A is the vector, B is the vector. But look at over here. I've once passed 0, 0, once I passed 0, 1. What does this mean? This means that if I am standing from the 0th index, I can have 2 options. You can either start off by saying I was initially at energy drink A, that would mean you are at the 0th row. Or you can say I am at energy drink B, that means you are at the 1th row. So that is the 2 possible cases to start off with. Hence, whatever is the maximum out of these 2 possible cases, I print the answer, because I want to maximize my energy gain from the drinking. Alright. Now, what is the base case? If I goes greater than equal to n, obviously I want to return 0. That would mean I have exhausted the total, all energy drinks have been exhausted. I can move on. Else, let's say I did not memorize this first. I'll not memorize this. Let me show it without memorization. So what I'll do is, no memorization right now. Let's see. I'll say currently I have an energy 0. If my row is 0, then I will add on the ith energy drink, energy drink from the A array of the ith hour. Else I will add on the energy drink of the ith hour from the B. And then I have 2 options. Option 1. This is option 1. Skip and shift. That means I will skip the I plus 1th hour and make my row to be whatever different row it was. So if let's say I was at row 1, not of 1 would be 0, so I shift to 0th row. If I were as row 0, then not of 0 would be 1, that means I am now at the 1th row. So skip and shift. This is option 1. Option 1. And what is the other option? Other option is not skip. When you do that, what does that mean? You shift only to the I plus 1th hour. That means you only jump to the next hour and you don't change your row, so row remains as it is. This is option 2. Now, what about the final solution? Solution would be the current energy you gained plus what is the maximum of both these 2 options. If you skipped and shifted, what was the answer from that? I will take the max from that. Or if I did not skip, then what was the answer from that? And this is the recursive solution. Now, if I want to memorize this, very simple. I declared a dp. I'm maintaining 2 states, I and row. So what I'll do is, if I and row already have an answer together as a state stored in dp, I'll return that. That's point number 1. To not you calculate every time each and every answer again and again, I can use pre-calculated solutions. That's the purpose of dp. And the other thing would be, once I'm returning this memorized state, I will also declare that this I row was equal to that value, so that I can utilize this once I move on. So then together now I know that I have a total time complexity of, as explained, n into 2, or simply you can say n. O of n would be a decent time complexity, because n into 2 means n only. 2 is a very constant factor in this. So if you don't consider the stack complexity that can come from this recursive solution, then you are good to go. And this definitely works. It gives you the right solution. So that's going to still work. So what about the time complexity? I can say time complexity is in order of n only, or n into 2 to be very specific. And what about space? Obviously, I'm using a DP, right? DP has a total space of n into 2. So this is again n into 2. So in a time complexity of n into 2, or basically order of n, and in space also in order of n, I have formed a recursive to a memoized solution. All right. So I hope this definitely catches up with the beginners. If it doesn't, I do recommend you that you stop over here, maybe practice some, or go through some basic knapsack problems where we sometimes take, not take, or create or not create, where we basically have 2 or 3 options. This option identification is sort of a very simple thing in DP. It does come up a lot of times in Leetcode problems and in very standard problems, and this was one of them. All right, good to go. Let us move on to the third problem. All right, so problem 3. Now up till here for this contest, I feel that the first 2 problems were pretty easy. I mean, the second problem might not be a very beginner based problem, but then this third problem was actually very, very tricky, and there was a lot of case making. So I'll try to show you the observations I did and how did I come up with utilizing and understanding that this could have been done to get the correct answer. And let's try to see if there is any doubts in that part, right? So you can definitely ping that in the comments and I'll be ready to answer them. All right. So find the largest palindrome divisible by k. You are given 2 positive integers n and k. An integer x is called k palindrome if x is palindrome, very obvious, and x is divisible by k. So now the logic is you need to return the largest integer having exactly n digits, that is k palindromic. So that means you need to return some integer. When you convert that integer to string, or even if you don't, you just look at it, you understand that it's palindromic. And if it's palindromic, it should exactly have n digits and it should be divisible by k. Now this is a very, very important property. Now, when I looked at this question, my first intuition was to look at the constraints. If you look at the constraints, n is very large, agreed. But if you look at k is only till 9. That means k can only be the possible 10 digits in the number part. Not 10 digits, possible 9 digits in the number part. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's all k can be. So once I read the question, my first solution in my mind was, can there be some observation to this question where I can brute out all the possibilities for each and every k, maybe make cases, a lot of casework. I know that would have been much more intricate during the contest and pressureful, but that is how I solved this problem finally. So what I did was I understood that since k is so less and it's only covering the basic digits, that means all I am trying to do is somehow figure out the divisibility properties of all the different 9 digits and finally get the correct answer. So if you look at the test cases, let's say n is 3 and k is 5. So we have printed a number 595. Now this is palindromic. Why palindromic? For all the beginners out there, what is the meaning of palindrome? Palindrome simply means something that's read as it is from the front and from the back. So let's say I have a string A, B, C, D, C, B, A. If I reverse this out, it's still A, B, C, D, C, B, A. That means it's a palindrome. This is from the front, this is from the back, and it's still a palindrome. It's still reading same. So it's a palindromic string. So if I talk about the integer 595, if you look at from the front, it's 595. If you look at from the back, it's still 595. That means this is a palindromic x integer. Now 595 has the other property that it's n equals to 3, it's the 3-lengthed integer, and for k equals to 5, it is divisible by 5. Good to go. All right, and the argument is this is the largest we can form, hence the whole part. All right, cool. So now that the problem is clear, let's try to observe some very, very simple things. All right, let's try to make case work. So what I'll do is, I'll use up a lot of pages in this. I'll say k is equal to 1, k is equal to 3, k equals to 9. My first observation was, if you have been given a n-lengthed integer you need to print, and it has to be palindrome, what is the largest integer you can have? Largest integer can be, obviously, n times 9. If let's say n is 4, then can I print 4 times 9? Is this the largest integer I can create? Yes. And is this palindromic? Yes. 9 from the front, 9 from the back. 999 from the front, 999 from the back. So if I have an n-length integer that I want to create, and it has to be the maximum in value, then that means I'm simply going to print 9n times, and it's going to give me the correct answer for that largest integer. But the other condition is it should be divisible by k. Let's now look into this. Tell me if I have an integer that's all nines, some n nines. Will this integer be divisible by 1? Your answer will be yes. Every integer is divisible by 1. So if k is 1, whatever n is given to you, will it bother you? No. Can you say that if k is 1, I can simply print n 9s and that will give me the largest possible integer, that is palindromic? For short, that's palindromic. Yes, I know, for short, that's palindromic. But it's also divisible by 1. So for k equals to 1, can you argue that I am good to go? I have very clearly formed k equals to 1 case. Answer would be yes, I am good to go in k equals to 1. Now similarly with k equals to 3. Tell me, if a number has to be divisible by 3, what's the property? The property is the sum of the digits of that number should be divisible by 3. Yes? So if I have a number 9 plus 9, sorry, 9, 9, 9, 9, 9, 9, 9, so on, so on, something, what is going to be the sum? The sum is going to be obviously n into 9. Yes, if I have some n 9s, then the sum is n into 9. Is n into 9 divisible by 3? Yes, it is. N into 9 is divisible by 3. Put it 3 below as denominator, 3 gets 3 and you get n into 3. That's the quotient. It's fully dividing. So what does this mean? This gives me next hint. If k is 3, then can I say that by the same logic, I had no need to check further for n, I will simply print n 9s. Yes, good to go. And then the final case in this, k equals to 1 is done, k equals to 3 is done, k equals to 9 is done, k equals to 9 is something we need to discuss. What about k equals to 9? Same thing. If I have all 9s, the sum is n into 9. If I divide this by 9, will it fully divide? Yes, it will fully divide. I will get a quotient of n. That means if I have a k equals to 9 given to me, do I need to make myself anywhere close to thinking, what should I further do? Can I just blindly be like, I don't need to do anything further. I will simply print, I will simply print n 9s and that will give me the largest integer, which is palindromic. It's of n size and it's divisible by k. Good to go. Alright, so now once I looked at this question and was able to, I came up with this thing within 5 minutes, right? I was able to understand that, okay, k equals to 1, k equals to 3, and k equals to 9 have direct answer, that's printing all lines. This gave me a boost, alright? If you thought up till here and you were trying to think something beyond this up till here, it gave me a boost. What boost did it give me? It gave me a boost that since k equals to 1, k equals to 3, and k equals to 9 were easily able to form by me, it means hidden somewhere in the question will be hints or hidden somewhere in the logic. I think I'll be able to also create for 2, 4, 5, 6, 7. These are all the numbers that I left. That's all. Yes. Sorry. I think 1, 3 was covered. 4, 5, 6, 7, 8. Sorry. Yeah. So I only now need to create my logic for these rest over case. 2, 4, 5, 6, 7 and 8. By some or the other interpretation, if I'm able to do that and do a lot of case making, I think I'll be able to do that. That gave me a confidence because I was able to create within 5 minutes logic for 1, 3 and 9. So that is where my mind headed next. I was like, all right, let's start with very basic. What about k equals to 2? I want to print an n-length digit integer, which is palindromic. So I again started off with the same ideology. I have total of n 9s. That's the largest I can go. This is palindromic for sure. But this is not divisible by k. Divisible by k. Because the divisibility power of 2 states that the last digit should be divisible by k. Yes? Now tell me, the last digit is 9. What is the next best digit I can use at this place which makes this whole number divisible by 2? Obviously, I don't want to make this 9 go very low. I cannot go above 9 because 9 is the largest digit. The digit just lower than 9 which helps me make this number divisible by 2 is 8. If I convert this number to 8, the digit to 8, will I not say that this number 9999998 is not divisible by 2? Yes, because it's an even number now. An even number is obviously divisible by 2. But, is this number palindrome? No. But because you change the last place as 8, will you not also will have to change this first place as 8? Yes. If you do that, now you know that the number is palindromic. So this is the ideology. If first I looked at k equals to 2, the property was last digit should be divisible by 2 or simply it should be even. So initially the last digit was 9. If I talked about changing it to the next best digit, it came to my mind that it should be 8 because that's the next lowest I can go, which will for sure make the number divisible by 2. But because this was 8 now, I need to fulfill the palindromic condition also. So I will also make this as first digit as 8. So that means it gives me a hint now that for k equals to 2, the best condition is to simply print an 8 over here, 8 at the end. That means 8 at the front, 8 at the end, and then whatever is the leftover consume space you can, that is total n minus 2 size, print all 9s in this. So print all 9s for total n minus 2 times, print a 8 at the front, print a 8 at the end. This is going to give you a total of n digited number, which will be divisible by k and which will be palindromic. And this gave me the next confidence that yes, k equals to 2 is also done, k equals to 3 makes sense. I am good to go, and k equals to 2 also makes sense, k equals to 2 is good to go. So this is how I was trying to build up my solutions. Now that you are catching up till here, if you're not, try to pause the video, go back in some 5 or 10 minutes, you will get the whole logic, right? And I would recommend you to follow this along with paper and pencil so that you're able to draw some cases on your own and understand the observation I'm trying to picture you out to. All right. So now K1 was done, K1, 3, 9 was already done, K2 was already very well tackled. Now K equals to 4. Now, first question, very simple. What is the divisibility property of 4? Divisibility property of 4 states is last 2 digits should be divisible by 4. That is, the last 2 digits, if they are divisible by 4, then the whole number is divisible by 4. So let's go again. I had something like 99999, let's say this much 9. All right. Now, if I want to change the last 2 digits to be divisible by 4, what can I go? Can I say 99? Like these are the last 2 digits I am focusing on. So my condition was from 99 I can go to 98. Is 98 divisible by 4? No. 97? No. 96? Yes, it is. So if 96 is divisible by 4, that means I can create the last 2 digits to be equal to 96. Yes. And because this last digit now becomes 6, I will also have to make this first digit as 6. This gives me a number 69996, and this is definitely a palindrome divisible by 4. But I did not stop over here. What I asked myself was, what about something more? What about something more? Why something more? Because it struck to me that if you go even below this, what is happening? Because you place the 6 over here, you also decrease the very high place of 6 from 9 to 6 over here, which led your number to go into the power of 60,000. Yes, this is 60,000. Yes. But what if something more? What if something more? Let's say I did not stop at 96. I went to 95, not divisible by 94, not divisible, 93 not divisible by 4, 92 yes divisible by 4. But again same thing. If I make this 92, then this number becomes 29992. Very, very small again. Stop. 91 divisible by not divisible by 4, 98 not divisible by 4, 89 not divisible by 4, 88 yes, this is divisible by 4. But what about this case? If you place 88 over here, then that will force you to place 2 88s over here. And can you see that? Is this number much greater than the numbers you were trying to form? Initially, we were having these two options. Either you create 6999996. You could have also created 2999992. In this case, you know they were divisible. But look at the first place, this first number. Over here it's 2, over here it's 6, over here it's 8. Obviously, this number is bigger than these two numbers, so yes or no? Yes. So that means this number was much more greater. If you could have not observed this very directly, what you could have done is, you could have run a brute force solution. I'll show that actually once I progress in the question. You could have run a brute force solution to further iterate in your idea. So when I looked at this observation, it made sense to me that the best ideal case is to go to 88. Not below also, because if now I go even below this, let's say 84, then same thing. I will have to place a 84 over here, so 48 over here. So now this numbers goes in 4 order, 40,000 order. If I want to still keep it a very high order, that's the 80,000 order, that's the highest I want to go, then it's the best case is I use 88. So my observation for k equals to 4 was fulfilled, and it told me that your best ideal solution over here is, what can you do? Let me just increase the eraser. Let's go back to 5 over here, I think. Yeah. And the eraser, I want a bigger eraser. Cool. Yeah. So what was my observation? I said, all right, cool. If this is the case, then what should you do? You can have 288 in the front, 288 in the back. And whatever is n minus 4 left at this position, print all 9s. Print all 9s over here. Yes, does this make sense? Agreed. So if in this case, if let's say, even in the above case also, if let's say n minus 4 was negative, that means you did not had the capacity to print these 9s, then you could have simply printed all 8s. Yes, that would have been the correct case. So if let's say n minus 4 is less than equal to 0, then you can simply print whatever is the n number of 8s. If let's say n is 3, print 3 8s. If n is 2, print 2 8s. If n is 1, print a single 8. If n is 4, print 4 8s. But after this, to make your number go very large, always insert a 9 in between, because that will keep your number as high as possible. And you have already made sure that the last two digits are divisible by 4, because that they are 88. So if they are the 88, then you know the last two digits are divisible by 4 and you're good to go. You have also maintained the palindromic thing, because if last is 88, you have also kept the first as 88 and good to go. So this created my case done and dusted for k equals to 4 also. Okay, so k equals to 2 was done, k equals to 4 was done, and now all I had to left was to form a solution for 5, 6, 7 and 8. Yes, so what I did was I moved on to 8. First I moved on to 8. Why? I'll show you. So 8, k equals to 8 has a similar property like k equals to 4. That's why I moved on to this. K equals to 8, for 8 the divisibility is the last 3 digits should be divisible by 8. That's the property for k. So if the last 3 digits have to be divisible by 8, isn't this the same thing as the last 2 digits had to be divisible by 4? What did I create over here? 88. Very easily I understood that in this case, all I need to do is, if last 3 digits can be made 888, then it's divisible by 8, and then first 3 digits can be made 888, and then rest n minus 6 numbers can be 99999, so on. And this gives me a beautiful number that's n digit total. It's divisible by 8 and definitely is palindromic, because I have 3 8s in front, 3 8s in middle, and then all the 9s. So 3 8s in the end and all the 9s. So k equals to 8 case was also done and dusted. So once I formed 4, I was also able to create 8 quickly, and I was done and dusted with the general possibilities. So 5, 6 and 7 were left. Now my next focus went to 5, because that again easy divisibility property to check. 5 simply states the last number should either be 0 or it should be 5. The last digit should either be a 0 or it should be 5. So let's start again. You have 999999999. Yes. And let's say this last digit has to be converted to either a 5 or 0. So I kept it as 5. I said, all right, if I keep it as 5, then this also becomes 5. So the number now I have is 5, all 9s and then another 5. Now, if this would have been a 0, then what? If this was 0, then this would also have been 0 and this would have been 99999. Now tell me, if I go any below than this, will I create a better solution? No. Because if you have the first digit at 0 now, the total number has decreased by a 1 place only. Initially you were total talking about 9 digits. Now you're talking about only 8 digits. So you decreased a digit. You know always that a 9 digit number is going to be greater than an 8 digit number. So is it possible for me to make a 0? No. So very quickly I was able to observe that the next best thing should be, for this case, next best thing should be that you make a 5 in the front, you make a 5 at the back, and in the front and the back, and the rest n minus 2 places can be filled with all 9s. This dusted off my k equals to 5 case also, and I was good to go with this case also. Only left were 6 and 7. Now I focus my power on 6. All right, let's go on to 6. Very interesting. So this is where like 6 and 7 were a bit tricky. 7th was the most trickiest. I think up till here you were able to catch up very well. If not, pause the video, form some test cases on your own. You'll be able to easily understand what I'm trying to picture you out, and you only will be able to argument that yeah, what I'm saying is right. I cannot make better case than this. So let's go to k equals to 6, a bit tricky. Let's look. Start off with n 999 and so on. Let's say I took total of, let's say, 10 9s. All right, good to go. Now what will happen is, so let's say I have 10 9s. Now I know the sum currently is looking like somewhere like this, like n into 9, or if I have 10 9s, you can say 10 into 9, so on. Now for k equals to 6, the divisibility test is should be divisible by 2 and should be divisible by 3. If it has to be divisible by 2, very simple. From the previous cases we saw that I can convert the first digit to be 8 and the last digit to be 8. Voila. Now I know that the number is divisible by 2. So I total have the sum now as 8 into 9 plus I have 8 into 2. Yes. Now I know if I divide this by 3, which is the divisibility test for 3, divisibility test for 3 says the sum of every digit or total digits in this number should be divisible by 3. Is this divisible by 3? No, not at all. It's not divisible by 3. What does this mean? It means I need to change something. Now my next observation was, if I need to change something, I need to obviously either increase the sum or decrease the sum. Currently my sum looks like this, 8 into 9 plus 8 into 2. Either I increase the sum or I decrease the sum. I know I cannot increase the sum. If I increase the sum, I will be violating this condition. I know I don't want to increase the sum. So this place is now fixed. I will not hamper these positions. Whatever I need to do is do somewhere in between this. So that first thing, it maintains palindromic structure and the sum reduces. If it reduces, I get the order. So first I have to observe this. 8 into 9, that gives me a total sum of 72. Plus this is 8 into 2, that gives me 16. Add this up, this is 88. If you do 88 mod 3, what do you get? Will I not get 4? I'll get 4. What does this mean? It means that this total sum currently is up by 4. If I'm somehow able to decrement the net sum by changing some digits to come below or exactly 4 less, then this whole number will come divisible by 3. So that is where my mind started looking. So first of all, I asked myself, do I want to change this number? If I change this number, then it hampers a very large number because I know this is a very higher place. This is like one of the rightmost places. So I don't want to change these places. If I look over here, this middle places are something I can hamper with because I know that this total number has a length of even. If this total number has length of even, I total 10 digits. So can I change this middle 2 places? How do I change them? If I make them as 7 and also I make this as 7, will I not decrement my total sum by 4? Because initially they were 9 and 9, now they're 7 and 7. So 9 plus 9 was 18, 7 plus 10 was 14. So you decrease from 18 to 14 in a net sum. That means now your total sum isn't looking like 8 into 9, it's basically 6 into 9 plus 8 into 2 plus this is 7 into 2. And if you add this up, now you know very well this gives you a total sum that's 84, which mod 3 gives you 0. So if we observed over here that if we have a even lengthed number, that is n mod 2 is equal to 0, then the ideal best case is to place 2 7s in the middle, 1 8 and 1 8 at the very end, and then whatever is n minus 2, sorry, not n minus 2, I can say n minus 4 by 2, this number of times 9 over here, and n minus 4 by 2, these many number of times 9 over here. This is going to give me the best possible case. So I tried to dry run this also. Like I formed up my own solutions. I said, all right, when n is 4, when n is 6, when n is 8, when n is 9, 10, 11, and I found that this case was definitely working. So what was the other thing? The other thing that hampered was if I need to maintain the palindromic structure, the other case in this again is, what if n mod 2 was equal to 1? That means let's say initially you start off with the same thing. You say I had, let's say 9 ones, 1, 2, 3, 4, or 7 ones, 5, 6, 7, 7 ones. Now try to hamper this. If I want to make this divisible by 2, same thing, change this 8, good to go, divisible by 2. But what about 3? Currently, the sum is 9 into 5 plus 8 into 2. Add this up, this is 45 plus this is 16. Add this up, this is 55 and then this is 61. If you ask me now, mod 3 is 1. That means this total value of sum is only up by 1. If I make one small change in a single digit, let's say this middle digit changes to 8, will I still maintain my palindromic condition? Yes, because the middle digit, if it's changed in an odd digit integer, I know palindromic feature still remains. And does the sum reduces by 1? Yes, it reduces by 1. So now the total sum turns out to be 60. And 60 mod 3 definitely gives me 0. Yes, good to go. So what was the other case for k equals to 6? K equals to 6, other case was if n mod 2 is equal to 1, then make a 8 in front, make a 8 at end, make a 8 at middle. Then whatever is the number of leftover ones, that is n minus total, I can say, this can be called as n minus used up 3 positions. So you can say n minus 3 by 2. These many number of 9s over here. Similarly, n minus 3 by 2. These many number of 9s over here. And I again formed a lot of, like, this is a very direct observation I'm telling you because I don't want to expand the video a lot, but I would very well recommend you to sit down with a pen and paper and make these cases and you will definitely come up with this idea. All right. So once this was done and dusted, it was a bit tricky, but I was finally able to figure this out. I got for k equals to 6 also. So now all that was left for me to do was for k equals to 7. Now this was the most trickiest part. I was not able to get any pattern in this because k equals to 7 has a very sort of a very not pattern based property. For k equals to divisibility test of k equals to 7 is basically that if you have a number n, let's say the number n is, let's say, like 999. Then the divisibility test says is you remove the last digit, double it, and then decrement that digit from the leftover position. So you say 99 minus 9 into 2, that's 18. This new number that comes should be divisible by 7. This is the divisibility test of 7. I know it's very bothering. All right. So once I googled the divisibility test of 7, it came to me very quickly that I will not be able to form any pattern just by pen and pencil. I need some more conclusion to this. So what was my next solution? This is some recommendation I'm giving you for beginners also. All right. Again, I know that the solution can be maybe like the problem can be solved by some very intricate DP. I'm very well aware of that part, but I did not want to go into that area because observations is something you need to have a practice on, because this is kind of like an ad hoc problem. So ad hoc problems requires a lot of observations. All right. So my next observation was, all right, I need to create some pattern. To create a pattern, I need data. Without data, how can I create a pattern? That means the data should be, I need the answer for n equals to 1, n equals to 2, n equals to 3, n equals to 4, n equals to 5, so on till whatever limit I can go in my boundation, I need that answer. If I get somehow the correct answer for n equals to 1, 2, 3, 4, so on, maybe I can look at that series and maybe I can figure out some pattern. But the first thing was, I need to get that pattern. So how do I do that? Obviously with the help of code. So what I did was, I'll show you. I wrote up a code for myself. What did I did? I took a very simple for loop from reverse order and I wrote a is palindromic condition where I would have first checked is the current number palindrome. If it is that number also dividing k? If it is, then I would print that number and return. That would be the first place from the backend side, iterating from the highest 9s to less than equal to 1. And then what I did was I ran my brute force for each and every test case till my compiler failed. So I noted those observations down. First I ran for 1, 7. That means n is 1, k is 7. K always went 7. So once I ran that, I made this I equals to 9 over here because I want to go to maximum this much. So I said starting from I equals to 9, that's the highest n length I can go, answer is 7. Good. So I noted this, that for n equals to 1, answer is 7. Good, great. Now I switch this. This becomes 2, this becomes 99. That's the highest I can go. So I again wrote the solution. I said, all right, for 2, 7, answer is 77. Good to go. Noted this down. Then again, I did this. I read this as 999. I changed total digits can be 3, ran the solution. I received the solution as 959. And then I did this, and I received all the possible answers till 15. After 15, I started getting TLE because once I took 16 total and 9 digits, it turned out to be TLE. And this is where my compiler failed. This is where C++ indirectly failed. That means I was able to collect the data from this much position. Now, once I collected the data from this much position, look at the observations. I'll actually show you my observations. All right. Look at there very neatly. Once I look at this data, I understood that there has to be some repetition. Why? Because my intuition was like, if there is no repetition, there has to be there will be a very randomized answer, and it won't be very possible for me to calculate a randomized answer for such a third problem only in Leetcode. Why would there be a randomized answer? There has to be some pattern. So I was fully focusing on finding a pattern. All right. So I actually found a pattern. Look at the pattern over here. Once I exceeded the limit of 12, that is this place over here, I started to observe that I'm getting back, let's say for like a 0-digited answer, you know that you had an empty string. So like nothing for n equals to 0. Now let's try to see. This is like an empty space. So I'll underscore this out. It's an empty space. All right. So after the 12th place, what was happening is, if I look over here, the 12th place, I have 6 digits over here. I have 6 digits over here, right? 6 9s over here, 6 9s over here. Let's bifurcate over here. In this middle, I have nothing. That's emptiness. This emptiness is basically at the 0th position. Now look over here. In the 13th place, let's bifurcate the 6 digits over here also. And let's bifurcate the 6 digits over here also. What is this 7? Isn't this the answer to 1? Yes. Again bifurcate. Let's bifurcate. I have 9 over here, 9 over here. What is this answer 77? Isn't this the answer to this 2? Let's bifurcate again. I'll actually zoom this out. Let's bifurcate again. Take out 6 9s from here, 6 9s from here. Answer is 9, middle part is 959. Isn't this the answer for 3? Yes, is that right? Yes, that was right. So now because my compiler failed after n equals to 16, I was in a mindset that now I need to utilize some other language. Either I could have utilized big integers in Java, some big library in C++, or Python. Python has a very good handling of approximately 100 to 200 digits. So what I did was, again, I'm repeating this again, this is not a beginner friendly problem. Either way, even if you go by DP, it's not a beginner friendly problem. If you don't, it's not, because if you don't have very small knowledge of how you can write up simple you can say Python function to create this thing out, it's going to be a problem. Again, I did not create any extra Python function. What I did was simple. Now, up till here, my idea was that if my condition is right, then the next number should be look like 6 9s, then 9779, that's the answer to 4, and then 6 9s again, and this would have been the answer for 16. So my all I had to ask Python was, is this number divisible by 7 or not? And that's what I did. I simply said, let me copy this number, let me go to the compiler, and let me ask Python, is this number divisible by 7? And when I ran it, to my surprise, it turned out to be 0. That means if this number is completely divisible by 7, that means the correct answer for 16, for n equals to 16, should have looked like this. Same ideology, for 17, the answer should have looked like this. That is 6 9s over here, and then 99799. That's the answer to the fifth n in the middle. Checked again. Is this particular number divisible by 7 again? Checked it. Asked Python, because it can handle large numbers. So I asked it, yes, very well, turned out to be mod 70. That means answer is right. What about 18? Checked again. What about 19? Checked again. What about 20? Checked again, and so on, so on. I checked up till like 35 to 40 places. I don't want to do that on video right now. But once I did this, I was fully convinced that if my cases are not falling till 40 places of the series of this 7 divisibility test, then I know for sure I am getting the correct answer. I am working in the right intuition, the right head mindset. So this is where I said, let's just write the code for it. If it gets accepted, fine. If it doesn't, let's maybe change my idea. And it did get accepted. All right. So this is the whole idea I have followed for k equals to 7. All right. So now I have discussed all the k's separately, right? So what I'll do is, let's try to quickly look at the code so that we can revise each and every case, and we'll see how did we manage that out. All right. All right, cool. So let's again start off. Initially, we discussed what k equals to 1, 3 and 9 together. We said if k is 1, 3 or 9, you no need to think any further, simply print n 9s. So I created a string of n size of total 9s, all 9s, and returned it. Good to go, k is done and dusted. Now k equals to 2. If the size of the n is less than equal to 2, then I'll print 2 8s or 1 8. And if it is not, then what do I want? I want 1 8 in the front, 1 8 at the back, and then rest n minus 2, total 9s in the middle. So this is what I did. 1 8 at the back, 1 8 in the front, n minus 2 9s in the front, in the middle. That's what I did. Now for k equals to 4, next case condition discussed. If k is less than equal to 4, print all 8s. If not, 2 8s in the front, 2 8s in the back, all the 9s in the middle. Case done and dusted. For 5, as we discussed, for 5, what did I do? 1 5 at the start, 1 5 at the end, all 9s in the middle. If n is less than equal to 2, print only all 5s. K less than equal to 8, same condition. If k is less than equal to 6 this time, why 6? Because I had total of 6 limit inside this. Print all 8s, else 3 8s in the front, 3 8s at the back, and all 9s in the middle. Now the most tricky two cases. First, let's look at k equals to 6. If k equals to 6, if n is less than equal to 2, I'll print 2 6s. Alright, I think I did not discuss this. I'm so sorry. I skipped this part. So again, when I was making more cases in k equals to 6, I also realized that this condition is not going to get fulfilled if I am standing at less than equal to 4. So like n less than equal to 4, I was forming some different cases. So I brutally forced that out by using this logic only. Like I had written a formula for myself only. All I had to do was make this like over here you can say very well, like let's say I make k equals to 6 and I make this, let's say I want to for n equals to 4, then I simply run this. I'll make this actually as 999, that's the highest I can go, and I'll print this. So I will receive a number that is 877. So I just brutally said that, all right, if n equals to 4, print 8778. If n is 3, print 888. If n is less than equal to 2, print all 6s. That's the case. So if n was, let's say, total of 99, and n is 2 and I want to check with k equals to 6, then the answer I received was 66. That's why I said, all right, if that's the case, then I know I'm running a best solution over here from the reverse. If it's giving 66, that's the best case to go. So I printed over it. But after this, now my logic followed. The logic I explained, that now I know that if I was at an even position of n, so if even, that means I'll go in the else part, n mod 2 is 0. If I'm at even position, I'll be printing 1 8 at the front, 1 8 at the last, 2 7s in the middle, and then n by 2 minus 2 9s in this position and also in this position. Same thing, if n mod 2 is equal to 1, that means I'll be printing 1 8 at the front, 1 8 at the middle, 1 8 at the end, and all the leftover positions to be filled by 9. That is n by 2 minus 1 position to be filled by 9. And this covered up my k equals to 6 case. Now came the best trickiest case, that was for k equals to 7. First what I did was I created my options. I knew that my options are getting repeated after 12 places. Over here I saw, right? Till 12 places I was good to go. So till 12 places what I did was I calculated all my answers. I said for 0 the answer is empty. For n equals to 1 answer is 7, 2, 77, 3, this, 4, this, 5, 6, 6, this, 7, this, 9, 6, so on till 11 this. Now I want my answers above this. So first I calculate L, that's n by 12. This gives me the number of complete 6 9s segments that can be placed on each side of the palindrome. Then I calculate n mod 12, that gives me the leftover in the middle part, which I want to calculate. So the whatever comes in the middle, this middle thing, right? What is that part? And then I can convert that into strings. First I calculate all the 9s. So I increment 9s by L times. Then I want all those 9s first times in the front. Then same number of 9s in the back. And in the middle, whatever is the R value, just extract that from this unordered map and print it, concat this everything and return it out. This gives me the correct answer for 7. And this is what finally worked with me, and it ran, and that is all the case making I did. Again, I did a lot of case making. This might seem very easy now that I have told you this could have been done, this could have been done. I very well recommend you to sit with your pen and paper, form your cases on your own, practice this question again so that you finally get the logic and it's clear through your head that ad hoc problems require this level of observation. All right. Now, what about the time complexity? Obviously, I am running a time complexity where I am creating strings in n order to return for every case. If case 1, 2, 3, 4, so on something, that means overall time complexity is simply O of n, right? I am simply creating n lengthed string for me to print. What about space? Only in the case of this unordered map where I'm taking this space of extra 12 spaces to create this for k equals to 7 is where I'm getting a space. Again, 12 space is not very high. So I can just ignore that part. I can simply say I don't require a lot of space. So I can say space is almost constant. So in an n order, now I have created my answer. All right. So very, like I can say a very ad hoc based problem, definitely a hard rated problem, not at all for beginners. For beginners, I only recommend you to solve different ad hoc problems before you encounter this. If you are right now watching this, try to make your own case problem, try to observe and remember what observations I told you, rebooting it out, writing your own piece of codes to check your own reverse theory. Like I wrote my own piece of code, right? I wrote my own piece of code to reverse engineer my own theory and understand whether what I was thinking was right or not. So all this also is done. Like people also do this. So doing this part, all this comes into picture when we solve ad hoc problems where pattern-based observation is required a lot. All right. So this completes our third problem. I hope you liked it. Let's move on to the final problem. All right, so the final problem 4 actually, count substrings that satisfy k constraint 2. So this is basically the second part of the first problem. All right, and this was actually a very hard problem for me to think also. All right, so we'll try to keep it very basic, and I'll try to show up what intuition can fall in my head. But then again, this is not at all a beginner friendly problem. So let's see what we can discuss and how do we come up with the solution. All right. So as the first problem was there, it's kind of the same problem. You are given the binary string S and you'll be given the integer K. But in the first problem, you were not given any queries. Over here, there are some queries. What they are saying you is, you will be given 2D integer queries, that is queries of I from Li to Ri. And in that Li to Ri, you have to answer that what is the number of this correct k satisfying substrings in that. And the conditions are same. If you think that a binary string is satisfying the k constraint, then either of the thing has to hold. Either it has at most k zeros or it has at most k ones. And then you count that total number of strings and that becomes answer of ith query. And then you have such answers to be printed for each and every query, and then you report that answer vector, that's the integer, return an integer array answer, where answer of I is the number of substrings for each and every query. Alright, so now this problems become pretty hard now. So what is the thing is, now that you know that the strings is, first of all, string is very huge, string is not at all in 50 order, first point. Other point is, you also have queries, so you cannot calculate in a brute manner for each and every query. Alright, so you are given queries in 10 power 5 order, and otherwise the question remains same. First calculate the answer in, let's say, 0 to 6, let's say you want the answer in 0 to 5, 1 to 4 range, 2 to 4, 2 to 3 range, and so on. So otherwise the logic of how initially a string would look like and how that is called a case constraint remains same, but the whole complexity has to be played along with. Alright, so let us try to have some very crude observations. Like in these questions, in these sub questions, what is my first intuition is, what is the time complexity am I targeting? Alright, so let's look into that. Obviously I have a queries length that is in 10 power 5 order. To process the queries, I would require a for loop which goes to each and every query and then answers that. Yes, so that means I will have a O of Q order already in my queries. Agreed? Yes. Now inside this, if I run a logic that is, let's say, working in O of N order, just assume, let's say O of N, will this work? No, because you have a Q into N order, and that would be in, since N is also in 10 power 5, that is, not N being basically size of the string. So if N is in 10 power 5 and queries already are in 10 power 5, then you will run into a 10 power 10 order and you will get a TLE. That means you cannot form this solution. It's not going to work. That means we need something lower than this. So my next mind that ran was, the next lower time complexity of the inner logic can be reduced down to log of N. If I have a log factor of complexity, whatever code I write inside this, then I will get a complexity of Q log N. And Q log N complexity would mean I have something like a 10 power 5 into log of 10 power 5, which means like approximately 10 power 5 into 20 iterations, like log 10 power 5 is like 17, 18 something. So that still gives me a 10 power 6 order, which is good to go. And even better than this, like if I can go even better than this, then the best thing next to this would be that inner logic runs in constant time complexity. So better than log n would be if I have a constant time complexity, then I am for sure good to go, because I know now my time complexity would only be O of Q, and O of Q definitely works. So my mind ran in this logic that I need something that's log n will be fine, or even constant, that's fine. But since log n is giving me more space, more time complexity, more things to play along with, that means maybe log n is something I can first put my energy into. So now when we look at log n, one thing that comes into picture is binary search. There is like normal binary searches work in log n order, and problems like this actually give, by experience, I can say this, that normally problems like this ask you, if you're going for a log n order inside the logic, then somewhere or the other you're running a binary search, because a binary search is helping you run a log n order, and that is helping you calculate the answer. So my other intuition was, that means maybe somewhere inside something binary search is something like that is getting run, and it is helping me calculate my answer quickly. Alright, now let us try to have some quick constants and observations that we can create. Alright, so let's say I have this string. This string is 0, 0, 0, 1, 1, 1. 1, 1, 1, 1. Okay, 7 length. Alright, so n is basically 7. So what will I do is, I know that I can run a 2-pointer sliding window. I can run, again, not beginner terms, so I don't want to make it much more complex, but using a 2-pointer approach, 2-pointer sliding window approach, what I can do is, I can calculate that for each ith index, what is the leftmost index for which, let's say that index is index L, for which L to I has valid substrings. Just try to catch up with the idea, and you will finally get why am I doing this. Alright, so I know that by 2-pointer sliding approach, what I can do is, I can very well calculate that for each index I, let's say I'm standing at this index, let's say this is the ith index, what is the most maximum index I can go, where if I stand, the total mid substring will have all the valid substrings inside it. That means no substring inside that substring will not be valid. That's the case. That is something I want to calculate. So how can I do that? A very simple pointer based approach. I'll say, all right, let me run like a for loop from int. Let's say this is the right pointer. Right pointer is 0. And then right pointer wants to move on to the very last position, that's n. And then right pointer is plus plus. Yes. And then what can I say? I'll have a 0 count, that's z. I'll have a, okay, something like 0 count, that's 0. And then I shall have a 1 count, that's also 0. Then what can I say? I can say that, let's say, I will first check, is s of right equal to 0 or is it equal to 1? If it's a 0th character, then 0 increases by 1, right? 0 increases by 1, 0 plus plus. Else I'll say 1 plus plus. Good to go. Now, if I know there is a left pointer also with me, the left pointer is also at 0. So 2 pointers, right is the pointer and left is the pointer. I have 2 pointers. Now I know that while 0 is greater than k and 1 is greater than k. That means if you are standing at a current right pointer, you incremented your 0 count and 1 count by 1, but your net 0 and net 1, both of them increased so much that they went above k. Then till this is correct, till this value is correct, this loop is correct, you will have to bring your left forward. Right now you were incrementing your right to go forward, but now you also have to backtrack and, not backtrack, bring your left pointer forward. So how will you do that? You will say if s of left, if this is equal to 0, then you will decrement your 0 by 1. Else you will decrement your 1 by 1 counter and you will increment your left by 1. Now what happens when you come out of this while loop? When you come out of this while loop, can you argue that you will be standing at a right index? One pointer will be at a right position. Let's say this is the string. S1, S2, S3, so on till Sn. So that means when you come out of this pointer, you will for sure be standing at, let's say a right pointer will be here. And the left pointer for that corresponding right position will be at a location where you know for sure that this is the leftmost left position where I knew that let's say this is the left. So if this is where my loop would have ended, I know the between substring from this has all the valid substrings. So I can create a previous sort of an array where I can say my right, for previous of right, my answer is left. All right. So now let us try to dry run this on the case itself. So the test case is 0, 0, 0, 1, 1, 1, 1. So what will happen is I have an initial array, 7 positions, all empty. All right. I will try to calculate the answer. So first right starts with here. This is right. This is right. And then this is also the place where there is left. So when right is at the position 0, count of 0 is 0 right now. Count of 1 is also 1 right now. And for this test case, k was 2. So now you incremented 0 by 1, 0 became 1. Now tell me, is 0 and 1, are both of them gone greater than k? No, they haven't gone greater than k. That means till this r, the leftmost L that's possible is also 0. So r was also 0. This is 0, 1, 2, 3, 4, 5, 6 position. This is also 0, 1, 2, 3, 4, 5, 6 position. So you will say that for this R0, L was also 0. So I'll save for R0, L0. That would mean that till this index, the leftmost index which I can go, for which I will find all valid substrings, is 0. Now move on. R becomes 1. Counter increases from 0, 0, 0, 1. This becomes 2. Now you have 2 zeros and 0 ones. Now do you think the conditions are false? No. The conditions are still good to go. I know I am good to go. So will I go inside this while loop? No. 0 is greater than k, 1 is greater than, no. 0 is less than equal to k, it's still 2, and 1 is definitely less than 2. So I am still going to remain, I'm not going to increment my L pointer, it still remains at that position. And I know that would mean for R equals to 1, the leftmost position for which I still find valid substrings, like this region, is actually total 0. So I still save 0 over it. And that's true because I know that if you chunk up this area, if you chop off this area, this substring 0, 0, the substring 0, 0 if you extract all the possible substrings out of 0, 0, it's going to be 0, 0, 0, and 0. 3 substrings. All of them are valid. Yes, all of them are valid. I know the condition is still fulfilling. All right, good to go. I hope you are able to catch with this part. Now R changes. R moves on. R is at this position. And then zeros go to 3. Now zeros have gone greater than 2. Yes, but ones have not gone greater than 2. They are still less than 2. That means I still don't increment my L pointer and this value is still 0. Move on to R. Now 1 changes to 1. 0 has gone greater than 2, but 1 is still less than 2. That means I'm still good to go, and for this L doesn't change, L still gets saved as 0. Move on to R1 over here. 1 becomes 2. 1 is still less than equal to k. 0 count is greater than k, but 1 is still less than equal to k. So 1 condition still holds. That means I am still good to go. So I'll still save this as 0. And now you pop over here. Now see, you have 1s as 3. Now 1s have also gone above 2. 0 counts have also gone above 2. That means you now need to bring your L pointer to forward. So you will bring it from 0 to 1 and you will decrement this L 0 position. That means now your 0 count is going to go back to 2 because this gets crossed off. So when this gets crossed off, now your L is at this position, L equals to 1. And now you know, since 0 has become 2, which is not greater than k anymore, you break out of the while loop. You break out of the while loop and now you can save L equals to 1, which means that up till the R equals to or index equals to 5, the best valid chunk was till L equals to 1. In this chunk of region 0, 1, 1, 1, if you take this region 0, 0, 1, 1, 1, you draw with your pen and pencil, you will for short come up with all the substrings from this string being valid. That means I'm good to go. Next time, move on R over here. That would be at this position. So 1 count turns out to be 4, but still 0 is still satisfying the condition. I still save L equals to 1. So now my previous array looks something like this. Previous index sort of something, whatever you can call this, like we can better name this in the coding part, but it looks something like this, which means that if I have some value over here, then that would mean that till that ith index, what's the best previous or leftmost index I could have catched for which between that region, everything was valid. Good to go. Now try to follow up. Why did I do this? Or obviously your question would be, why are we doing this? Why are we calculating this previous array? I'll take one more constant on this and then you will realize why am I doing this. Alright. Now on top of this previous index array, what am I going to do? I am going to do one more thing. What is that one more thing? That one more thing looks something like this. I am going to calculate a prefix sum on valid lengths sort of an array. Right? What is the meaning of this? This array would represent what is the total count of valid substrings till ith index. Now how do I do that? Very easy. I have this previous index array. Yes. So if I have 7 positions now empty over here and I want a prefix. So can I say I will not first create a prefix. I'll only calculate till ith. So tell me, till this position, what is the total number of valid strings? Can you say 0, that's this position, minus 0, that's the previous you can count, plus 1, because that one character that's not getting counted, that's 1. What about till this position? Can you say 1 minus 0 plus 1? Yes. So can I say 1 minus 0, that's going to be 1, and plus 1, it's 2. Good to go. For this, 2 minus 0 plus 1, that's 3. That means till this position, the ending, till rth ending, I can know I have total if I want till ith index to be ending, I know there are 3 substrings that could have ended on this ith index, which would have been valid. One string is this, one string is this, one string is this. All 3 are valid. Yes, I am calculating this and then I'll calculate the prefix. So 3 over here. 3 minus 0 plus 1, 4 over here. 4 minus 0 plus 1, 5 over here. 5 minus 1 plus 1, that's 5 again. And 6 minus 1 plus 1, that's 6. Now calculate the prefix on that. So if I calculate the prefix on this array, this becomes 1. This becomes 1 plus 2, 3. This becomes 1 plus 2 plus 3, this is 6. 1 plus 2 plus 3 plus 6, this is 10. This is 15. This is 20. And this is 26. So now I have an array. Let's remove this array totally. I now have an array which represents that till a ith position, what is the total number of valid substrings. So if I say that over here, like this is I0, 1, 2, 3, 4, 5, 6. So if I say that at the position 415 is stored, what does it mean? Physically, what does it mean? It means that till the 4th index, this string total 00011 would have given you a total of 15 valid substrings. And you can calculate that by hand also, you will receive the same answer because logically it makes sense. Yes. So now I have calculated two arrays with me. One is this array, which helped me calculate this array. Now the main problem starts. We'll ask ourselves, why am I utilizing or why am I calculating these two arrays in the first place? How is it helping me calculate my answer? All right, let's go into that part. All right, now I know very well that I want to solve each and every query in log n time. So let's say you are given an R. Let's say, sorry, you are given an L and you're given an R. All right, in between this, you have L plus 1, L plus 2, so on, so on, so on. And then this is R minus 2, this is R minus 1, so on. So this is the range you are trying to calculate for. Good to go. So what am I going to do? I know that I have calculated a previous index array. That means for every index, I know what is the leftmost position till which there are valid substrings. So tell me this part. Let's say you pick up a position over here. Let's say you call this position as mid. For this mid position, if you ask from this previous index array, where is your leftmost? It is going to reply to you with a valid number. It's going to say, all right, if I asked what is the leftmost previous for 4, then it would have said 0 is the leftmost previous for 4. So I know that if for 4 I ask and the answer is 0, that means till the 0th index, I will find the valid substrings. Before that, I'm not finding valid, but till that, everything is valid. Every substring, if I calculate in between that, make in between that, form in between that, it's valid. So if I'm standing at a mid index, I ask myself again, for this mid index, where is the leftmost previous? Now, there can be two possibilities. The two possibilities can be, let's say this position, this reply that I get is some position, let's say pos. What can happen is, for this pos position, or let's say for this pos position, what are the two things? Since pos is the leftmost part, leftmost index where all valid is found, condition 1 can be pos is coming before L. Yes, because L is the maximum limit you can go. So condition 1 can be pos comes before L. Or condition 2 can be pos comes greater than equal to N. Or pos comes less than. These are the only two conditions that can come. Either pos can be so low that it goes before L, or pos can be so large it goes greater than equal to L. All right. Now let's answer this. Let's say that I want to find the first place mid where pos is greater than equal to L. Meaning, I will ask myself, where is that first mid position in this set of L to R for which the previous best index was greater than this leftmost query? Why do I do that? First of all, let's try to think, if I want to find this, can I find this in log n complexity? Answer would be yes. Why? Because you know that for this previous index array, can you see this is monotonically increasing? Yes. You have 0, 0, 0, 0, then 1, 1, 1. Can you ever imagine this previous index array to be decreasing? Will it always increase? Will it always be an increasing array? Yes. Why? Because the left pointer is always increasing. Initially started off with 0. Then what can happen? It can go to 1, 2, 3, 4, so on. It can never decrease. Like once left has increased, it will never decrease. And you're always making previous or right to be left. So the left values are created in such an order that they're always increasing. By this observation, I know that if for this mid, let's say for this mid, I find a value, previous value, which comes over here. Let's say this is the position it comes. Let's say this green position I'll mark. This is where it comes. So for mid plus 1, can I say that this position is going to shift a bit to the right? If for mid, it was at this location, then for mid plus 1, it will either be at this location only or something to right. Then for mid plus 1, mid plus 2, it's going to be up more something to the right. Then for mid plus 3, bit more to a right, and so on, so on, so on. That means, yes, there would be one such location, there would be one such fine mid for which its leftmost position would be just greater than L. It would fall somewhere over here, just greater than equal to L. Yes. And that is the position after which every position is going to give me true. So if I would have asked you through a checker function that for this mid, do you think the previous most is greater than equal to this leftmost query L? Then if you would have replied true for this query, then every query would have been true after this, and every query before this would have been false. Because if for this the answer would have been false, everything before that also would have been false. So this is the monotonic predicate nature on this mid. That means I can binary search to find the first place where a true occurs, or the first place where I actually find the leftmost index for that mid position to be above the L-most query. I hope this is clear. Now, next question, very simple question. Up till here, if you are able to catch it, now arises the main question. Why? Why am I doing binary search? Why am I calculating this? This is the main idea. All right, let's look again. So let's say there was this L range, this R range, and you're able to find this best mid position for which the position lies, let's say, greater than equal to L. Then what can be the case? This pos is obviously going to lie between L and mid. So it can lie either exactly at L, that's one thing, or maybe it can lie over here. That's the other thing. Yes, somewhere between L to mid. Now let's assume it lies over here. So you have L plus 1, then let's say this L plus 2 was actually the position, L plus 3, then your mid over here, then L plus 5, let's say, so on. Then this can be R minus 2, R minus 1, and R. Any problem? All right, cool. Now, what I will say over here is, if you're standing at this pos, you know that for this mid position, the leftmost best was at this location. So any number that is mid plus 1, mid plus 2, so on, all those pos values will be greater than this. They will come over here, or over here, or over here, and so on. So now tell me, if I ask you, what is the count of, like my target is to count the total valid strings coming between L and R. Can I bifurcate this into two subqueries? Can I say, what is the count of valid substrings coming between pos and R? And what is the count of valid substring that comes between pos and L and pos minus 1? If I calculate them, then can I add it up and that's going to be my answer? Answer is yes, that's going to be my answer. But the problem is, first of all, how do I calculate this? To calculate this, let's look at query number 1. Query number 1 is very straightforward. You know that you have a prefix lengthed valid query. You have all the valid substrings till every index. Till every index, you have the total count of all the valid substrings. So if I ask you that you need to calculate for this region of segment, can you say that region of segment will be this minus, total of this, that is till R, minus till pos minus 1. That is the segment I was talking about, and in that segment I will get all the valid substrings, and that gives me the answer to the first query. Now what about query number 2? Now I know that any pos before this, like if this mid was the first place for which pos was greater than equal to L, then any mid minus 1, if this pos, I calculate the pos for mid minus 1, it would be before L. It might come over here, or maybe come over here, or maybe come over here, definitely before L. So if it's coming before L, that means all the region that lies over here, I can just write what is the total length of this region. Let's call that total length of the difference region as diff. Then can I say that diff into diff plus 1 by 2 is actually the total varied type of substrings I can create in this segment, and that would be all valid. Why? Think like this. We know that for mid, the best position till it was valid was pos. For mid minus 1, it would have been some pos which came before L. So this leftover region from this pos to this L, it's definitely valid. So obviously then from this region to this range would also be valid. So if you form any substring between this region, from this L to this pos minus 1 actually, then can you say that any region from pos to L to pos minus 1, any substring I create in between that will be valid? So if any substring will be valid, all that is left for me is to calculate the number of substrings. And I know the number of substrings for a region of, let's say, a region of, let's say, size S is actually S into S plus 1 by 2. That's actually the formula also for number of natural numbers, and that is where this comes from actually. All right. So I can use this formula to calculate the diff. First diff is this region. Let's say this region turns out to be this length. Diff into diff plus 1 by 2. This is the answer to this second query. And the answer to the first query, it's simply calculating prefix of R minus prefix of pos minus 1. That would give me this difference. And this difference will also be correct because this will encapsulate all the possible valid substrings that could have lied. So now in log n time complexity, first I find the mid. Then, because I had already calculated prefix, now it answers a question. You must be thinking right when I was talking about the prefix array. Since I already had a prefix array calculated with me, I can now quickly answer in constant time complexity. What is the number of valid substrings in this region? That's query number 1. And over here also, I can very easily in O of 1 time complexity simply calculate the difference and then number of valid substrings. That would be answer to query number, division number 2. So something you said, bifurcation I did for query 1, query 2, and then add 1 plus add 2. That gives you the answer for L to R valid strings. All right, L to R region to create valid substrings or valid K constrained strings. All right, so again, a very, I should say a tough problem otherwise, right? Definitely a tough problem. You should definitely pick up your pen and paper and try to dry run this out on some or the other case so that you easily get a hang of this. All right, so what we can do is actually quickly try to see if we can run a solution on this part. All right, so let's actually run on this thing, right? What we followed over here, what we followed. We had calculated something that looks like this, right? 1, 3, 6, 10, 15, 20, 26. All right, so I'll actually note this down. 1, 3, 6, 10, 15, 20, and 26. And over there, I had calculated 0, 0, 0, 0, 0, 1, 1. This is what I calculated. So this was the previous arrays and this was the prefix sum arrays. Now, the query that we were asking was for 0 to 6. All right, cool. So 0 to 6 query. I make this as L, make this as R. Find the mid. Mid will be R plus L by 2. 6 plus 0 by 2. That is simply, you can say 3. So mid is 3. So this is the indexing 1, 0, 1, 2, 3, 4, 5, and 6. So I'll check. Currently, when I'm standing at the third index, is the best left, is it greater than or equal to L? Yes, it is. So that means answer for this is true. I can move a bit forward. All right, I can definitely move a bit forward. So since answer for this is true, that means everything after this is also true, and I need to shift my R to mid minus 1. So I'll say after this, the answer is also always obviously true if at this location, the leftmost of this is actually this, that's 0. 0 is greater than or equal to 0. That means everything after this is obviously greater than or equal to 0. Yes, it is. You can see this 0 greater than 0. This one definitely greater than 0. This one definitely greater than 0. So I can move my focus to the search space mid minus 1 and find it again. So I'll say, all right, 0 to 3. 0 plus 3 by 2, that's 1. Find for 1. 1 is the new mid. For 1, answer is again true. So that means everything after this is also true. Again, 0 to 1 by 2, that's 0. Answer is 0. Yes, condition is true. And this is where I stop. That means the first index for which the previous is greater than or equal to L is actually 0 index itself. So if it is 0 index itself, what will be the bifurcation? Bifurcation will be from here to here. And here to previous is not present at all because you're only standing at L. So you just calculate the answer between prefix of R minus prefix of L minus 1. That means 26 minus 0. That is why the answer totally turns out to be 26. So like 26, that is prefix of, you can say prefix of R. That is R in this case is 6 minus prefix of, you can say L minus 1, right? Or 0 minus 1. Since this is 0, I don't remove anything. So simply this is basically like 0. Removing only 0 because you are standing at the very first index. So you can say it's typically 0 only. So you only remove 0 from this, which is basically 26, and that's your answer. Now you can obviously try to dry run this out on the better test case that's over here, and it is going to give you a very, very clear picture on what we are trying to achieve. All right. So definitely a complex problem, not at all which one come in a very good picture at all, and definitely not for a beginner problem, but I hope I was able to clear up the idea. All right. So let us look at the solution now. You have the size n. you have the answer vector, you have the previous index till valid strings are there, that's total size and vector, and prefix sum of valid strings vector. Now there's a left pointer, zeros count, ones count. Increment your right pointer, start with 0. If right pointer is 1, 1 gets incremented, L 0 is going to get incremented. If both go greater than k, then bring your left pointer forward by left pointer plus plus and make your previous index till valid of right pointer to be left pointer. That is saving that for this right pointer, the best place was left pointer. Now your prefix sum of valid substring starts with 0 being 1. Start off with 1, 1 is less than n. First calculate the length of the valid substring, that would be I minus prefix index till I plus 1. Basically this thing which I showed you over here, like let's say this is 1 minus 0 plus 1, 2 minus 0 plus 1, 3 minus 0 plus 1, 4 minus 0 plus 1, 5 minus 1 plus 1, 6 minus 1 plus 1. And when you do that, add that to the previous plus this current length becomes the current ith prefix sum. Now go to each query, first calculate R, first calculate L, Q0, Q1, result and the first position. Now first position, I initialized it with R plus 1, basically meaning that if I don't find an answer, that means my answer was basically R plus 1. Now I say that I run a binary search while R less than equal to L, calculate a mid. Is this previous index till valid of mid greater than L? That's Q of 0. If it is, this is Q of 0, that's L. If it is, then I know I'm going to make this first position as mid and make R to be mid minus 1, else R to be mid. L to be mid plus 1 because now I want to increment my range, right? Or bring my forward range, bring my range from L to forward and do not save any answer. But if that was not the case, then I actually get an answer. I save it because that's a true case and I move much backward in the direction from mid minus 1. Now, if this first position is less than Q of 1, that is R minus R, that is R. So if it's less than equal to R, that means I actually found a first position. If it is, I found a first position, then what do I need to do? I simply want to first calculate result of prefix of sum till R, add that. And if first position is there, then subtract from that first position minus 1. So basically this thing that if you calculate prefix till 6 minus prefix of whatever you could have calculated, and you can only calculate that if you think that the first position you found minus 1 is still greater than 0. If it is, then you're good to go, subtract that. And then this is like the basically the one part of the query, this one part I mentioned over here, and then this is the two part. Part 2. How do I do that? Difference, that's first position minus Q of 0, that's this region from L to pos, and then simply difference into difference plus 1 by 2. And then push back the result in the answer array, and that becomes the answer for the ith query, all right, or the qth query, whatever you want to call this. So now I know that the time complexity is going to look very well in my constraints. I know this is running in 2-pointer approach, which simply means this is running like a 2 into n sort of an approach where I know left and right pointer both can traverse the whole string. So this is 2 into n, which approximately is n only, right? And then I have a prefix loop over here, that's also n. And then I have a queries loop, which is running in Q, but inside this I have a binary search that runs in log n, right? So I know I have a total complexity of, you can say complexity TC is O of n plus Q log n, in which the greater term is obviously Q log n. So I can call this as Q log n, which is approximately can be written as O of 10 power 5 into log of 10 power 5. And this gives me the correct answer. And what about space? Am I using any extra space? Yes, I'm using a prefix array of n size and an answer. So I can say this is going to be n total space consumed. All right, good to go. So I think this solves the whole problem finally, and this is where we can end our post-contest discussion. So I hope you liked the video and the post-contest discussion. Thank you for watching.